Good evening. I'm David Zwerdling.
I'm Gina Griza.
Thank you for joining us. We'll be talking about the atomic add function in x86 ISAs called lock-add.
We're going to talk about why lock-add exists, then we'll talk about how lock-add works, and next we'll look at some performance timings of lock-add, and finally we'll look at the ways lock-add might affect programmers on a daily basis.
Let's begin by talking about why lock-add exists and the problems it solves.
Add functions as you would expect. It's a binary operator that performs the arithmetic add operation on the values in its arguments and stores its results in the location given in the first operand. The first operand can be a register or memory location, while the second can be a memory address, as long as the first is not, or it could also be a constant.
This talk will focus on add in the cases where the first operand is a memory location. That means that it will be reading from that location in memory and writing back to it with the result of the operation.
When we use add on a memory location, we have to consider a less local operation. We need to include the ALU and registers as with any other register local operation, but also the entire cache bus from local L1 or L2 all the way to the shared L3, DRAM, and even beyond.
Because of the access to the memory locations, the load step to move the first operand into a register could transit L3 or DRAM. That could take somewhere between 4 and hundreds of cycles. The add operation takes a relatively short amount of time, and then the value is written back to the memory location. These are caches, so it's possible the time could be very short between the load and the store, but it could also be very long.
But modern CPUs don't have single cores, and they have more complexity to deal with because of it.
In a multiple core system, values from DRAM can be cached at multiple different places, like in individual cores L1 or L2 cache.
Consider this example. Here, two cores have simultaneously started running an add on the same memory address.
First, each core loads the memory address's value into each of their respective L1 caches.
Then the cores perform the calculation.
Then the cores store the values back. So in this case, performing 1 + 1 + 1 = 2.
But it should be 3. That's a race condition.
We need a way to implement exclusive memory access. That's atomicity. x86 assembly provides the lock prefix. Using lock means the next instruction gets the exclusive access to the memory address.
That's pretty abstract. Let's talk about specific methods we can use to prevent concurrent writes to identical memory addresses.
One way we could implement lock is to just disallow other access to memory. But this is slow since other threads of execution don't get to perform their reads and writes while the CPU is locked. That's a big deal for a multi-core system. It's overly broad. One process might prevent others from accessing memory only it knows about, even though the data is only referenced in that process. Intel stopped using this method after the Pentium 6 and associated ISAs. What they implemented in the so-called core architecture in 2006, they moved to a cache level lock. Instead of locking everything, in a cache level lock, the cache maintains its own inter-cache coherence. In order to dive deeper into the way these things are implemented, we have to switch gears for a moment and talk about cache consistency.
This class discussed caches following 2 ways of maintaining consistency with main memory. Data can be written back when each line is modified or when the line is evicted. Remember that the first option, write through, will write more than necessary since it's probable that the data in DRAM will not be immediately read back. So caches generally implement a write-back method of ensuring backing memory is consistent. This is implemented with an additional bit in each cache line, which maintains whether the cache line has been modified, or colloquially, a dirty bit. From here on, we'll call it the modified bit.
Or M for short.
In a multi-core environment, though, cache synchronization is a problem. If we want the advantages of a write-back cache, there must be a way to make sure the lines that reference the same addresses are synchronized, like in the race condition earlier.
When a cache is loaded a line from memory, but hasn't modified it yet, it should accurately reflect DRAM. It could also be loaded in other caches. A shared line must never be dirty, and shared lines are read-only. But the line's data can still be held in multiple caches at once. So now we need a way for other caches to know when other caches modify a shared block. There needs to be a way to synchronize our caches so that when something which is shared is written to a local cache, other caches will still know about it.
Most architectures implement bus snooping. In bus snooping, each cache listens to the shared higher level bus for requests to their modified blocks. If there is a read from another block, the modified block is supplied and marked shared locally. There's more moving parts than are shown here, but this is sufficient to keep a multi-processor cache coherent. Another method of maintaining coherence is to keep track of the caches where each block is mirrored. This is the cache directory method, but x86 doesn't implement that. Before we move on, keep in mind that an invalid state is represented by 2 states in our table. That's just wasteful.
Messi further refines the MSI protocol by adding an exclusive state to each cache line. When the line is marked exclusive, the local cache has the only copy of the data. When a line which is exclusive is written to, other caches don't need to be notified. That means that there are fewer transactions on the bus for the bus snoopers to interpret. When another cache reads the line which is held in a local cache, the local cache still changes the line to shared, so that non-local caches get a notification if it's changed via the bus snooper and invalidate their associated lines. On the whole, Messi lowers the throughput of bus snoopers. Processes that do not act on shared data benefit massively from this exclusive state. This exclusive bit can also be encoded with no extra space.
In the MOSI protocol, if the processor can maintain an additional bit in each line, we can add an owned flag to the potential states. In this state, the cache indicates that any requests for the data should come from it rather than the DRAM. This further reduces the number of reads from DRAM.
Let's review the concurrent add operation from earlier, but this time on a MOSI-enabled platform.
The 2 L1 caches both try to load the same memory location, just as before. But this time, the memory bus arbitrates the 2 requests and, in this case, gives the load to processor 0. And because of the lock flag, when processor 0 loads the data, it marks the line exclusive. At this point, processor 1 will be blocked from reading the data via a cache bus implemented locking mechanism, so processor 1 will wait.
Now, processor 0 will perform its calculation.
And when storing, having modified the line marks it as such.
As processor 0 ends its lock, it flags its data as owned. This requires processor 0 to serve requests for the data from its local cache instead of main memory. If other processors had the data in an unlocked operation, their cache value would be loaded from processor 0's cache. Also, if the line was evicted, it would write back just as in a normal write-back cache.
Now, the cache bus serves processor 1's locked load request with the data from processor 0's cache.
It marks it exclusive
And invalidates processor 0's line.
at which point the calculation takes place just as before in processor 0. After all that, The data will reside in processor 1's cache as owned until it is evicted and flushed to memory or invalidated by another processor's exclusive request, as happened here. Modern AMD 64 platforms implement MOSI, but MOSI is not the only way to implement multiprocessor cache coherency. Intel experimented with the MESIF protocol, for example, where a cache could hold a read-only forwarded version of the cache line. And there's Mercy, where the cache lines are marked as recent when read from memory. That was implemented by Apple, IBM, Motorola, and later Freescale between 1999 and 2005. The rest of the protocols listed here essentially are variations on the previous ones mentioned, with other variations on how the cache line transitions between each state.
In summary, x86 assembly gives the lock modifier for assembly programmers to be able to do various atomic operations. When lock is used, the hardware uses special flags in the cache to maintain cache coherency, so programmers get a memory-consistent multiprocessor environment.
Next, let's look at some performance characteristics of lock add.
To test the speed of lock add, we wrote and ran timed benchmarks. For each benchmark, we created an array of one particular type of integer, atomic and non-atomic. Then we iterated through the array and performed an add operation on each element, either in order or randomly, but once for each element. Then we verified that each element had been correctly changed. We tested each combination of atomicity and searching order at 30 array sizes, 100 times each, achieving statistically significant results. Testing was done on a modern CPU, a Ryzen 9 5900X with SMT enabled, which implements the MOSI protocol.
These are the timings we measured. A lower number means the test group took less time to execute and was therefore faster. Let's dissect the data a bit to understand why each of these measurements is what they are.
Atomic operations incur more overhead for the core. If we normalize the data pairwise by atomicity, we can see the result of that. Non-atomic operations are almost 4 times faster regardless of ordering method. You can see that spatial locality plays a role in the speed of the operation since the non-atomic accesses were less fast than sequential, which is something the class talked about a while ago. Essentially, don't use atomic unless necessary.
Finally, let's review the way to use atomic and how we can use it in higher level languages.
In assembly, all you need to add to use the lock feature is add lock in front of the instruction. Lock also works for a number of other instructions. For example, CMPX-CHG as discussed in class.
If you're interested in using higher level language, GCC will compile the lock feature in x86 when programming in C using the _atomic type specifier in advance of your type.
And it turns out that other systems languages follow this pattern too. The implementation may differ for some of these languages, especially since the higher level options on this slide have implementations of their runtime environments outside the x86 platform. But the implication is the same. In order to write race-free code, the platforms here give programs robust memory access. But when you run on or compile to other platforms, they may not have advantages of AMD 64's ISA and might have other disadvantages.
Thank you for listening to our talk.
Thank you.